Hello and welcome to tutorial 5 of Let's Learn C for Beginners. So in this video I will end it up with our end result of Goomba Invaders for the Commodore 64. But first off, I think I might have strayed a bit off course with some of the order of things. So I will start off with going over bit operations and bit masking, and then comparison statements, and then I will go over the Rect structure, which is used everywhere for simple collision detection between rectangles. Everything basically is rectangles everywhere. And then I will also, after that, I will then go over the state machine, which is a design pattern, the state pattern, which is very useful in coding, as it's the backbone of the main game loop. And then this will also feed into the Goomba Invaders game as well. So first off, let's go over bit operations and masking and why you would need to use this. So if you remember on the first video I did, I went over talking about binary and the parts that make up 1 byte, which is 8 bits. And then each of those bits have a number going from left to right. So we have bit 0, which value is 1, bit 1, its value is 2, and there's obviously 8 bits in a byte, so that's 0 to 7. And then each of these you can think of as switches, and when they're on, that obviously counts as that value. And then obviously in a byte that enables the numbers from 0 to 255. So sometimes the computers not only use bytes as numbers themselves, but sometimes they can use them as flags or switches to indicate other tasks or events that need to be done. And this is where bit operations and bit masking comes in. So yeah, I've already spoken about that. So when computers need to carry out a load of different tasks, as I've said, sometimes they'll use individual bits to signal when a task should be carried out. So the registers inside, like a CPU, might use individual bits on a byte to indicate when it should carry out certain things or tasks. So what I'll do is I'll bring up the Commodore 64 memory map, as this clearly shows through various registers in the machine's memory how it relies heavily on bits. So here's an example here. The this register here controls the raster compare, which I haven't sort of gone into. In fact, the only ones I would kind of talk about here would be the smooth scroll registers. So you'll see that setting one of these bits basically is like flipping a switch to say do this to the computer. A key one here is this register here for sprites. So as I said in the last video, the screen on the Commodore 64 is 320 pixels wide. However, when it comes to sprites, so that the sprites can transition on and off the screen seamlessly, the coordinates of the sprites actually start off of the screen. So for sprites, the x coordinate 0 is actually to the left side of the screen by -24 pixels, and the y coordinate is obviously above the screen by 50 pixels. As the visible screen is 320 pixels wide, the whole x coordinate for one sprite is not going to fit in a byte. So what the designers did for the Commodore 64 was they added an extra bit for each of the sprite's X registers, and as there's 8 sprites, those 8 extra bits are packed into the byte at D010. So the extra bit for sprite 0 here is actually bit 0 in D010. So when you set this bit to 1, that would coincide with the x coordinate being set to 256, as in a 16-bit number, bit 8 is actually 256. And then for sprite 2, obviously it's called sprite 1 here, but it is obviously the second sprite, it uses bit 1, and then sprite 2 uses bit 2, and so on up to the last one here. So every time you set 1 bit on this D010 register here, that is actually the 8-bit of the x coordinate of an individual sprite. So this is where bit masking is useful, and also being able to test bits to see whether they're actually on or off. So you kind of really use this either when working with older consoles, so anything older than the it's a difficult one, because the Game Boy Advance, actually you use bit flags heavily there, the Nintendo DS also. So I would say, not including the handhelds, the main consoles, you're probably not going to be using bit flags much. On the Nintendo 64 or PlayStation 1 or later, anything earlier than that, including the handhelds but not including the 3DS, bit flags will be useful. However, if you are graphics programming or possibly sound low-level programming, then you might need to use bit masking again. So I think that goes over that. So now we need to kind of go over the logical bit operators now. I will jump into some examples to kind of clear all this up in a moment. We'll use the C in the browser to quickly demonstrate these. So excuse the spelling mistake here. The logical bit operators are just like their electronic counterparts. They are AND, OR, NOT, and Exclusive OR. They act like logic gates, switching on or off bits. So the ampersand here is used quite a bit in C, actually. You kind of have to kind of view it as in context. So if it's not used in a sort of compare statement, then the ampersand is probably getting the address of a variable. However, if it is in a comparison statement and there is just one, then it is most likely the Bitwise AND operator here. And then there's the pipe key here, which is the Bitwise OR operator. The NOT flag here. So this is the tilde symbol. That's the Bitwise NOT. It's rare that you'll probably use this. And this is the Exclusive Or symbol here. And then I also described here what basically about the Commodore 64 D010, so I've already talked about here. So let's go over the logical AND operator in C. So I will go to our C in the browser here. So let's quickly do some type defs. So we've got our unsigned char there, so we'll use some binary defines here. So just like you can define hexadecimal with 0h, you can also define binary with 0xb. So for example, if we print out the value of that, so we'll print it out in decimal there. Wait, have I put too many bytes in there, have I? No, I haven't. Okay, why is it not accepting that? Okay, I'm not going to argue with it. Again, why is it not doing that? I don't know why it's coming up with overflow there. So you see that that's 1 there. Okay, why is this complaining? Ah, I think that's why. There we go. Okay, I was putting the X in for some reason. There you go. So if I zoom in on here so you can actually... There you go. So you'll see that the 0B, not 0xB. There you go. So you can set binary numbers there. So I'll now show you the AND operator in use. So the way it works is, or the way you would kind of use it, is like this. So C equals A and B, and then you would print out the print out the value of A in decimal, value of B in decimal, and then we'll print out C in binary, and then C in decimal. So you see that A is 7 here, B is just bit 4, and then if you AND these together, you'll see that only bit 4 comes out of this. As the way that AND works is, if the bits in one byte and the bits in another are not set, then only the ones which are set will be sort of carried over. So you'll see that the AND flag gets rid of these bits here, as bits 0 and 1 are not set in byte B here. So one use for this could be, say we've got a load of flags set here in A, but we are only interested in the upper nibble here. Then you could say that B is masking out or removing the lower bits, and then you'll see here that if you AND 240 with any bytes, then what will happen is it will remove any of the lower bits. So that hopefully demonstrates the AND. So another thing you can do here is you can turn off A, for example. So you can say A or A equals A, and so what this would do here is this will also, in fact this will keep the bottom ones here and remove the top ones here from A. There you go. So you'll see now, if we AND A with 15, then it turns off all of the upper bits here. So you can either use it like this, or you could say A AND equals just like you could like A plus equals 5 or something like that. And then to print out A in binary. So we also put the .08 here. What this says is we want this padded to 8 zeros. There you go. So you'll see that A now, after we've done these operations, if I remove that, we do it again. So you'll see here that the after this here, this masks A and turns off the upper bits here. So that's how you would use the AND operator. So now let's go over the OR operator. So the OR operator, what that does is that will take the set bits from one byte or the other. So it basically merges them together. So you see here that A equals 207 here. B basically covers all of the top bytes here, so when these two are merged, you end up with C equaling 255. So if I do this a moment, make it look more interesting here. So you see here that A has these two set to 0, and then it has bit 0 set to 0, whereas B has some of the opposite here. So if we run that again here, come on, it keeps bugging out. There we go. So you see here that C has both of these bits here. Basically allows you to combine them. So you can say that the OR operator kind of is like adding them together. And again, you can use the OR operator either as like A equals or A equals A, or so let's go for 4. So I'll turn these off here. So what this will do here is this will set bit 4 here, and then this one here will turn on all of the upper ones here. So there you go, the bit 4 is now set. There you go, and then also F0 is all the upper bits here. So that's the OR operator. Now let's show the NOT operator. So this is one which I rarely ever use. In fact, I never use this one actually. So the way you use it is kind of similar, but you kind of have to use it slightly differently. So we would say that C equals not A, and then you'll see this is the value of A here, and then as C is not equal to A, you see that it has reversed the bits here. So all you would really use the NOT operator for when it comes to bits is just reversing them. I don't know whether you can, I don't know whether this will work, whether that's acceptable or not. No, it's not. So using it like this is fine, but you can't sort of do this to A, which is fine. So that's the NOT operator. So let's go over the exclusive OR operator. So that uses the caret or to the power of symbol here. So the way that exclusive OR works is it kind of works the same as OR, as in any flags which are on in 1 byte will be sort of carried over when they are sort of merged together. However, if all of the if in 1 byte a bit is set and that same bit is set in the follow-on byte, then they get turned off. So you'll see A exclusive or B here. Bit 3 here has been switched off. So I'll give you another additional thing there. Sort of 0 those two there. There you go, and you'll see that the bit 7 here has been carried over into C. Bit 3 has been turned off. Bit 1 is carried over, and so is bit 2. So you can also use A like this. So you see now that A and C are basically the same there, because you've exclusive OR A with B here. And then if you do this again, in fact, let's do a new line to try and make it clearer. So you see now, if you exclusive OR C with A, then it basically turns everything off. And then if we do that one more time, why is it not doing that? Oh, it could be because the window's not big enough here. Oh, there we go. So you see here, the exclusive OR, it kind of acts like a switch. So first off, these two are merged together. And then if you use the same value again on it, it turns all of the bits which were switched off back on. So you can kind of use exclusive OR like a toggle to turn bits off, and then if you use the same value again, then it will turn them back on. Hopefully that makes sense to you. You'll have to sort of play around with these things if you don't get what I'm trying to show you here. So the last operators I want to talk about are the bit shift operators. So what the bit shift operators do is this symbol here, these two left arrows here, these means shift all the bits in a byte, or a word or a double word, to the left So what that will do, if we come back to our bits here, so you've got your 7 bits here. So if you shift all the bits to the left by 1, then you've multiplied it by 2. If you shift all the bits to the left by 2, then you've multiplied it by 4. If you shift all the bits to the left by 3, then you've multiplied them by 8. So I'll show you this with A here. So we'll first print out the value of A there, and then we'll do there you go. So you'll see that by shifting the bits 1 to the left here, we've multiplied A by 2, so there. So you'll see here, these were the bits first off, and then you'll see here that the bits have been shifted to the left. So if we shift them by 2, then you'll see it is the equivalent of times in A by 4 now, and then by 3 there. That's the equivalent of multiplying A by 9. So you can also do the terminology like that, or like that. And then the other way is the equivalent of shifting to the right. So we will put A as 128 there, and then that basically divides A by 2 there. So to note that this is bits. So you see the significance of shifting bits here. This isn't the number free, it's bit free. So you see by this is the equivalent of dividing A by 8 here, as bit free is the number 8. So the on old computers, so for example I think all the 8-bit computers, they don't actually have any multiply or divide commands on the actual CPU itself. So there are no assembly commands on the actual chip to multiply or divide, so you have to do it yourself in code. However, if the number you want to multiply or divide by is equal to one of the bit flags, then this is a very fast way to divide or multiply. So as long as the number you want to divide by is any of these numbers, or another thing is, say you wanted to divide by 20, so 16 plus 4 is 20, So you can do 2 shifts. So if we say A equals 200, and then we first divide A by 16, and then do that. Okay, I don't think that's worked. I think it might be I'm not sure if you add them. Oh, I can't remember. Okay, I'm not sure whether you can. I think you might add these or subtract these values or something. What this should have equated to here, maybe, have I done this right? This is 16 here, so now it evades me now. So this, I don't know if you add them together, or I can't remember. There is a way that you sort of combine the results of these, but it escapes me right now, and I'm not searching for it because there's no point. You probably won't use it anyway. And if you are going to be working on the like Commodore 64 or old computers like that, then there are sort of ways that you can combine the shifts together. Unfortunately, this as this is this video is kind of on the fly here, I didn't think to include this, so that's it for bit shifts now anyway. So I will now move on to the compare operators now. So if you look online here, an easy way to sort of come up with it is you'll see that these are the symbols here. This is the Bitwise operators here, and this kind of gives you a vague description of what they actually do. The easiest way is just to play around in here, as long as it actually works for you, which it seems to keep bugging out for me here. But if you need to use them, that's how you use them. So now we will go into comparison statements, and unfortunately these the ampersand and the pipe keys are used again, so this is important to kind of know which ones to use. So unlike the bitwise statement, when you use 2 of them together, this is kind of like a boolean operation. What that means is the result is either true or false. So for example, so we'll say A equals 10, B equals 10, and then if A and B equals 10, I think it might have to be different than that. Yeah, that's not gonna. I think it's, so if A equals 10 and B equals 10, there you go. Oh, I've not put the data type in there. There you go. So God, this is bugging out a bit. So you see, we use, when they're both used together here, this is not carrying out a bitwise operation. This is just saying, is this statement true? And is this statement true? So this is how we would kind of use this in our own sort of language normally, and our own sort of everyday life. Is this thing true? And is this thing true? So you could do another here. There you go. So this is, so you can sort of put in as many different sort of comparisons as you need here, basically. This is just saying, is this true? And is this true? And is this true? So that's the AND operator here when it comes to checking the truth of a statement here. So you could say that one there, that would also be true. And then you could also have, so we'll use the NOT operator here. So this will also be true. So this, when you put the exclamation mark in front of the equals, that means not equal. So you'll see here, if A is not equal to C, which it isn't, so A equals 10 here. So if A equals 15 there, this should all result in false here. So this is still true here. So if we put that to 25, that's false now, because A actually is equal to the value of C. And then you could have, if you were going to use the OR operator here, so what we're saying, it's probably better to put these in brackets here as well, so it's more clear. So now we're saying, if A is not equal to C, or B is equal to 10, then this is true. So it's sometimes when you sort of have a load of compares, it's worthwhile putting them in brackets. The brackets basically tell the computer what order the compares should be operated in first. So it's doing this logical compare first. So the OR operator is basically one or the other. So it doesn't matter whether this one is true or this one is true. As long as one of them's true, then it will carry through. So now that should be false. So when it comes to the NOT operator, there's a number of ways you can sort of do it. So you can say not C equals A, or not C equals A. So those are the comparison operators there. I probably should have gone over this more in the one of the earlier videos really. It's obviously important to get those, and then there's also the greater than, equal, less than. So I'll cover those quickly as well, because again these are true or false here. So for example, if A is greater than B, there we go. So this symbol here means that the value on the left is greater than the value on the right. So if we switch those out for A and B here, A and C, you'll see that A is equal to 25 and C is equal to 25. And seeing as this is not true, then it results to false. However, you can use the equals here, which means greater than or equal to. And obviously that's C there, not B. There you go. And then you can also have the same the other way around. So that would be less than or equal. So if we put A as 26 here, you see that that's false because A is obviously greater than C. So that's the less than operator. That's less than or equal to, and then that's greater or equal to. These are obviously useful when you are trying to zero in on the value of one variable compared to another. Which brings us on to the rectangle collision detection. So in games, basically when it comes to 2D games, you can think of your sprites in a game or whatever graphical objects. They are always going to be inside a rectangle, one form or another. So usually what you would do is you would try and get a rectangle that closely fits the area you want to compare with. And then in our rectangle structure here, we would have an X and a Y coordinate, which most of the time refers to the top left side of a rectangle. And then you also include two other variables, the width and the height of the rectangle. And then the boolean operation rect overlaps or words to that effect are usually what you would use then to basically compare the corners of the rectangle to see whether one shape overlaps with another. So you're basically checking to see whether this point here is in between the left and the right points here, and whether it's in between the top and the bottom points. So you're basically comparing the corners against the corners in another rectangle, which is what this is kind of doing here. Although it kind of looks messy here. Basically all we're doing here is we are splitting out the points from one rectangle here. So you'll see AX here is taking the x coordinate in here. This here is only for you only need to kind of split this down if you're working on an old console here, as for example, as this function is being used on the Commodore 64. If you're using it on an 8-bit computer, possibly do the same on the Super Nintendo as well. What you do is you take these values here and you store them in a local variable, basically, because otherwise when you carry out the actual compare functions here, the computer has to find out in memory where each of these are and then compare that number, which obviously is very slow. Whereas if you first make copies of all the numbers and then do the compare bit here, oh, it looks like there's something missing here. Okay, not all the text is here. Oh, this doesn't matter anyway. I'll jump into the code now on the game and show you this working real time. So we are done with the browser thing here. So one thing to note with the game, in fact, I'll show you the game running first on the Commodore 64. And then I'll tell you the sacrifices I had to make. So here we go. Unfortunately, there is no sound. I run out of memory. The compiler didn't actually guard the graphic memory which I set aside. So you press the fire button on the joystick to play, and then unfortunately they do not shoot either, they just get faster and faster. Again, I was going to implement it, but I run out of memory. So this is the rectangle collisions working in real time here. So we have a lot of stuff in here actually. I had to remove some things as well. So I think there's 6 levels I've got in here. Obviously would have been nice to have some sound in here. So we have a full functioning game there basically, and I'll go over that now. So one thing I did was, in the last video you saw that we had all of this, all the data we set aside was all zeros. The idea for that was that's kind of like a placeholder for us to actually put the graphics directly in. So if I quickly show you the graphics which is in here now. So we have a full double height font set. Which is here. And then we have an amended standard font set, which is here. So the all these tiles here, the double height one is added after those. And then the Goombas here, they use a number of tiles as well. So you'll see each part of the Goombas actually takes up 10 tiles each. And then this gives us the illusion of them moving across 2 pixels at a time here. And that pretty much takes up, oh yeah, we also have the background blocks here as well. Again, I was going to have bases in which would protect you, but again, run out of memory. So you'll see that these take up another 8 tiles here as well. And then we have Mario as sprites here. So we have a number of frames of him walking here, and then there's one where if the invaders get too far down the screen, then he dies, loses a life. And then the explosions are also sprites. There we go. These aren't multicolour ones, they're just standard colour ones. And then basically all of the font set is added in here, and then the double height tiles are added in here. And then here are the background tiles. And then after those are the Goomba tiles. And then we have some spares here to pad out the remaining RAM before the sprites are added in at 3800 here. So there was a Goomba bullet. It was all prepared as I thought we had the memory guarded for us, but that wasn't the case. This was going to be the Goomba bullet here, what they would fire. There's a sprite for it. And this is how I laid out the game. Initially, this was the plan. So usually what I'll do is I will construct like a crude layout in pixels here. So each pixel actually represents one 8x8 tile. So you see here that it was 40 by 25, which corresponds to the Commodore 64's screen size. This was how things were going to be laid out here. This was not able to be done because run out of memory. And then here's our sprites here. So this file basically was, the idea was we would set aside a buffer in memory in the lower 16K of RAM for our graphics data. And then I had hoped that our graphics buffer, that the compiler would have worked around it. However, that was not the case. It just gives you a warning and glitches out when the program code actually goes into your graphic buffer. So I had to sort of do a new linker file here. I was trying to sort of resolve things, but it didn't work, unfortunately. The only sort of a workaround would be to try and put the graphics buffer a lot higher in RAM. However, that means you have to tell the Vic chip to look for its 16K window higher up in the Commodore 64, which can be tricky to play around with. So I just provide the game as is. The code is basically about 8K. So all I'm going to touch on in the game here is the first off, I will cover the rectangle collision code. So you'll see here we have our rectangle structure here. And you'll see we have two 16-bit numbers here. We have the X coordinate and the Y coordinate. The reason why the Y coordinate is a 16-bit number is because of how I implemented the invaders. As initially I run out of memory with them and had to creatively come up with a way how I could have them all use less memory. By all means, check this out here. Basically what I did was I created groups, or like a kind of vertical strips of them, where there was like a rectangle which kind of highlights where the group reside on the screen. It is a bit sort of technical, so I won't go over any more details here. By all means, have a look at the code to see how it all works. So we have our rectangle here, which basically, in the case in this game, it holds. So if I reboot this up again a moment. What I kind of did was divide the invaders here. So this here is one group, this is another group, and another, and so forth. So I use bit flags in here to indicate which ones of these are actually alive in that group. And then when you fire a bullet, the bullet rectangle first sees that it's inside a group, and then it scans over the bit flag inside to see which is alive, and then it will basically create another rectangle for each of these if it finds them to be alive, and do another compare there. It's also a way of increasing the speed there as well. Initially I was trying with an 8-bit rectangle, but as the group moves down the screen, the whole rectangle basically moves off the visible screen. So I had to promote the Y coordinate to a 16-bit number so that the collisions were working properly. So the rectangle overlaps function is the one I will cover. So I'll zoom in here so that you can actually see it if you are viewing this on a phone. So what we're basically doing is we have our two rectangles here, And what we need to do is we need to extract each part of the rectangle pointer. So we basically have rectangle A and rectangle B. So we have AX and AY and A width and A height and B's width and B height. And you'll see what we actually do for the width is we basically add the width to the X coordinate of the rectangle. So it in effect becomes the right hand side. And then we do the same for the bottom there. So we take the top coordinate, add the height to it, and that gives us the bottom coordinate. So we basically end up with a rectangle with all 4 points. So you can think of it as if I just fill this in here. So this point here would be left and top. This one here would be right and top. That would be left bottom, and that would be right bottom. And all you're doing is you are comparing these points to see whether they are inside a pair on the other rectangle. So here what we're doing is if the right side of rectangle A is greater than or equal to the left coordinate of X on the B rectangle, and the X coordinate of rectangle A is smaller than the right hand side of rectangle B, then we know that there's an overlapping on the X coordinate of the rectangles. And then if the same is occurring on the Y coordinate as well, then we know that both of them are actually overlapping, and then we turn true. Otherwise we return false. And that's the basics of the rectangle overlap function for our collision detection. So that is how we are sort of handling the collisions with our player here. So if we look here, we'll have in the player's code here, there is a hit function, and it basically takes a rectangle here. So the rectangle passed in here would probably just be the a Goomba basically. And then what we also have here as well is there are some collision offsets. So sometimes what you'll do with in a game is you'll set a collision rectangle to being smaller than the graphical shape of your sprite or graphic that you're using, and that's just so that the player doesn't feel that they've been unfairly collision detected against. And you see here the collision rectangle width and height is also smaller than the graphic shape as well. So if your collision rectangle is smaller than the graphic of your character, then you'll need to add an offset to that rectangle from the actual coordinate of your player, which is what that's doing there. And then you'll see here we basically set this temporary rectangle here to our collision rectangle, and then we check to see whether it overlaps with whichever rectangle has been passed to us, and then returns the result there. So in the game itself, if we look in the play code, okay, I think, yeah, the baddie manager actually references the player directly. So the collision basically takes place with the baddie manager talking to the player, I believe. Well, I'm not actually sure whether it's used. We might not actually be using that function directly. Okay, so that wasn't actually used. So the only collision rectangle functions we are sort of doing here is with the bullet manager here. So there is some of these functions were obviously put in here, but they were never sort of used in the end. So in the update code for the baddie manager here, so I think that is actually called in here. Here we go. Yeah, so this is the bad manager hit bullet is called in the main sort of play function here, and what that one does there is it basically gets, so the bullet manager here, it has a number of bullets. Some of them are designated to be the player bullet, and then others were actually designated to be the enemy bullets. Again, lots of it wasn't used because I ran out of memory, couldn't do that. So the bullet manager pretty much uses the rectangle collision in here. In fact, no, all it does is it returns the player bullet as there is only one of them. So what happens here is we have a rectangle for the player's bullet. This function here from the bullet manager returns the rectangle of the player's bullet, and then this grouped rectangle here is a temporary holder for the structure of the bad manager group here, which has its own collision rectangle. And then inside here, if the bullet overlaps with a group stripe, then we pass in the group ID and the bullets rectangle to this function here. And then what this does here is it also has a rectangle, and it basically recreates a rectangle for each of the invaders if they are alive in that stripe. And each individual invader has a collision rectangle of 32 by 16 pixels in size, which roughly coincides with its graphics in pixels. So if I bring this up again, you'll see here that the physical size is actually 32 by 16 in pixels, which corresponds to this size here. And then you need to take into account which offset value to use here. So there's an offset of 2 here, there's an offset of 4 here, and there's an offset of 6 here. So all of this is a bit more complicated for a beginner here, so I won't go over any of it, as this is only really sort of specific if you are wanting to look into programming the Commodore 64 itself. However, by all means have a play around, have a look over, try and understand what's going on. I will obviously provide the all of the source code and everything for you. The key thing here is the rectangle overlaps function, which is actually doing the heavy lifting really for everything, comparing whether things actually collide or not. So the only other thing I want to talk about in here is the state machine, which is running the main loop of the game, as everything else is probably too advanced at this time. So the way that a state machine works is it basically controls the flow of a block of code or a program. So this variable here basically handles which main state the game is in. So we're either at the title screen, so we have a function for title screen initialize, another one for title screen run, and then another one for game initialize and game run. This basically, with state machines, you can basically break up your program or project into key stages or areas, if you like. And then you say, if the game is in stage 1, do this. If it's at stage 2, do this, and so on and so forth. But only one of these stages or states can actually be active at any one time. And then it basically contains the way that a program works. So the state machine basically says something can only be in one state at a time. It's kind of like a design pattern is what it's known as. So for our game here, this is the main game loop here. And the core points, or the key thing I want to go over, is the state machine itself. So at the start here, we set the state machine to title screen initialize. And then we basically just have a switch statement with the various states that the game itself can be in. And then each state itself has a function to govern that state's code. So if we... First off, another thing I do as well is I try and split these states into their own sort of modules. So as these are game states, I probably should put MS here instead for like main states, but so you see we have our core functions in here declared, and then these game states headers and modules, they basically implement the states here. So the header file for the title screen is literally just going to be containing some things specific to the title screen itself. And then in the code for the title screen, you'll see we implement the main state title initialize function here. And then the title screen run function here. And then I change the state specifically inside this case here to transition automatically to the title screen run. However, to change the main state in here, the player basically has to press the fire button, and then we change the state in here. And then next time the main loop is updated, will then basically transition to the game state itself there, which has an initialize and a run function itself. So that basically is the main way you kind of want to structure your programs. Figure out what the key states of it needs to be, and then create some state functions here, and then some state IDs here, which you can access everywhere. And then you'll note that the main.h is included in the source file here, as anything which might need to reference the title screen itself shouldn't need to gain access to the main header file here. And then in the games header file itself, it also has its own state machine, because a game itself, the core mechanics inside there should be cleanly split into states. So we have new level reset, and then we have a number of states which basically are just sort of in between the actual gameplay itself. So usually they will be like you give a message to the player to say, you know, well done, you've cleared a level, or oh no, you've died, unlucky, and then you lose a life. And then if you do well, then you've won the game, or if you've done bad, then game over. And then unlike the main states, I also have sub-states, as in lots of these game states themselves. When you transition to them, you might have an initialization part that needs to take place first before anything else. So it might be you have to do a cleanup of stuff. So for example, if you've cleared the level, then you might need to hide or reset loads of the player objects before the next round begins, as an example. So here there are 2 substates in there. Again, you could have more if depending on the complexity that you wish to have. And then in here I also have like another load of messages here as well. That's kind of, it's another sort of state machine as well, really. So I'll quickly, I'm not going to go into detail on all of these states. Instead, I will kind of just sort of point that they exist here. So in the game itself, we have a substate there and a state there. So the state corresponds to one of these game states, and then the substate will be either at the initialized state or the run state. So for example, the get ready state here, when you call this for the first time, the substate should be set to substate initialize, and then in here you basically set the game message to get ready. There is like another state machine for the messages inside there. You then increment this substate. So basically you put it to the next one. And then in here there's like a timer which basically counts down. So it will wait for a bit for the player, or the player can skip it by pressing the fire button. And then either way, if either of these occur, so if the timer counts down to 0 or the player presses the fire button to skip, the substate is set to substate max here, which in this case means move on to the next game state, which here would be play the game. And then in here at the bottom we have the game initialize function here from main. This is pretty much bog standard everywhere. You basically set the this is like the beginning of the game. Basically you set the level to 1 or 0, set the starting lives, set the score to 0, and then you basically clean away anything which the title screen didn't. You then set the substate to substate initialize, and then the game state to new level. And then in the main state here, once this is run the first time, you change the main state to game state run, and then it enters into this state machine here, which handles the core states of the game. So those are the key things I wanted to just go over in this video. By all means, jump in and have a check out of the code for the game here. Play around where you can. Just be aware that the code in here is very tight. One thing to note though is most of this code, because it's coded in C, you can pretty much reuse most of it everywhere else. So although this game is obviously for the Commodore 64, because it's programmed in C, you could take it out and dump it onto anything. The only things you would have to sort of change would be how you do the graphics, basically. That would be what would change between one machine and another. So that's it for this video. In the next video, I will get back to more core C stuff. So in the next video, I will go over memory allocation, and we will also go into some file operation as well. So we will load a text file, save a text file, create a binary file, load that, save that, and that will be for the desktop. So that's it for this video. Thanks for watching. If you've got any questions, drop them below and I will get back to you when I can. Thanks for watching.